All right, hi everyone. Welcome to our 40th session of the MedAI Exchange. This week, we have Sabri Eyuboglu from Stanford here with us to present his work on discovering systematic errors with Domino. Sabri is a second-year CS PhD student in the Stanford Machine Learning Group, co-advised by Chris Ray and James Zhou. He is broadly interested in methods that make machine learning systems more reliable in challenging applications. To that end, he has recently been working on tools that help practitioners better understand the interaction between their models and their data. Thank you so much, Sabri, for joining us today. Before we start, could you let us know your preference about how you want to take questions?
Yeah, sure. We can maybe do questions at the end. I'll leave a good bit of time at the end for questions. That'll probably be the easiest. We can kind of have a discussion at that point.
Sounds good. All right, so let's try to make this session as interactive as possible. Without further ado, let me hand it over to Sabri.
Okay, great. Thank you so much. Excited to kind of present some of this recent work that we've been working on. So my name is Sabri, and alongside some other collaborators, I'll present some work on discovering the systematic errors that machine learning models make. So this is joint work with Maya and Khalid and some other really awesome collaborators without whom this paper and this work surely would not have come to fruition. So excited to share what we've been working on. So in this talk, we're going to start by formulating the problem of discovering slices of data where our models underperform. We call this slice discovery. And then afterwards, we'll introduce a quantitative framework for evaluating methods that actually solve this slice discovery problem. We'll discuss Domino, which is a new slice discovery method that we've developed. And finally, we'll conclude with some results and talk about some of the takeaways from the experiments that we ran. Cool. So I'm going to start out with an introductory example, and hopefully, I think probably many folks watching this will have seen some of these examples, but hopefully it'll motivate why we're excited about this work and why we think it's important. So around 2017, we started to see something really exciting. Deep learning models began performing clinical tasks that we previously thought only a clinician could perform. So for example, these models began diagnosing skin lesions, they began reading chest x-rays, and even detecting diabetic retinopathy. So this is a really exciting time because we started to imagine, the impact that these machine learning powered tools could have on an overburdened medical system. But it was also really concerning because what if these models were as accurate as a clinician on average? So they seem to be really performant, but actually they made systematic errors that a clinician would never make. So researchers started exploring this question in the context of collapsed lung detection in chest x-rays. So collapsed lung is a pathology that you can diagnose from a chest x-ray. Models trained to detect collapsed lungs achieved impressive performance on classifying this pathology from the chest x-ray, getting an AUC in like the upper 80s. This was very exciting. But the question was, were the model's errors distributed randomly, or were they perhaps concentrated in certain types of patients? So to answer this question, researchers started splitting the data set into slices. So what is a slice? A slice is just a subset of data points that share something in common. So an example of this would be all of the chest x-rays in the data set that are of children. So there are a lot of synonyms of this word slice, like subgroup, subpopulation, stratum, subclass. We're going to stick with the word slice throughout this presentation, and this is kind of the word that we use, but I think it's worth noting that this concept goes by a bunch of different names in the literature. Cool. So one interesting slice that researchers started to consider was the slice of patients with a chest tube. So a chest tube is a medical device that's commonly inserted to treat collapsed lungs. And when they evaluated performance on examples in the slice and out of the slice, they found a striking difference. The model performed significantly worse on collapsed lung patients that did not have a chest tube. Now, this is a really devastating finding in a lot of ways because this meant that the patients that the model was performing the worst on were actually the patients that still needed treatment, right? The ones that did not yet have a chest tube. So this story highlights an important fact about machine learning models. Even when they perform well on average, they may still underperform on critical slices of data. So since 2017, A number of papers have documented other underperforming slices in radiology ML systems, dermatology ML systems, as well as standard computer vision and speech recognition systems. The trouble is that in many cases, the slices are what we call hidden. This means that we don't know which slices the classifier might be underperforming on. And even if we did, we likely don't have the annotations necessary to compute metrics within those slices. So for example, most chest X-ray datasets don't actually have annotations telling us precisely which images in the dataset contain chest tubes and which images do not. So doing that analysis that we talked about earlier, where we compare the performance between these two slices, wouldn't really be possible. So finding these underperforming slices can be a really challenging endeavor. And indeed, all of these papers that we've listed here did a lot of really, really great work uncovering these systematic issues with machine learning models. But I think this makes me, and I think others, wonder, could all of this right here that people have discovered so far just be the tip of the iceberg? If it were easier to identify underperforming slices, might we find like a bunch of other model vulnerabilities, other issues lurking beneath the surface? So in our work, we set out to answer this question. Can we develop methods that automatically identify underperforming slices? And critically, can we evaluate how well these methods perform? So we call this task slice discovery, and we're going to walk through now exactly sort of how we formulate this problem and how we've been thinking about it. So we start with a labeled data set and a trained classifier, right? So the classifier is meant to be able to perform a task predicting a target from some input. Could be an image, could be like other unstructured inputs like video, audio, etc. So a slice discovery method is just an algorithm that can, given the data set and the classifier, automatically identify underperforming slices, that is, subsets of the data points in the data set on which the model performs less well than the rest of the data set. So the output of a slice discovery method is a set of slicing functions. So each of these slicing functions assign a value of 0 or 1 to each of the examples in the data set, 1 indicating that the example is in the slice, and then 0 indicating that it is outside of the slice. We can then apply these slicing functions to the data set and select the examples where the slice label is 1, and then evaluate performance on that subset and see whether or not there's a difference between the different slices. So in our work, we were inspired by a number of really exciting slice discovery methods that were recently proposed. So there's like multi-accuracy boost. This came out a few years ago. George, which also came from Chris's group, which is another really exciting work. And then the Spotlight, which is quite recent. And I think most similar to the methods that we started developing later, and is also really, really exciting. And I think we got a lot of inspiration from all of these methods as we were sort of thinking about the evaluation framework and also developing our own methods. Cool. So the thing is, though, when it comes to actually picking which of these slice discovery methods that we want to use, we want to first sort of think about what are the properties that we'd like our method to have, right? Otherwise, how can we kind of decide which of these different algorithms is best at doing the task for our use case? So for one, I think we're not interested in just discovering any slice, typically. We're interested in finding specifically the slices where the model is underperforming, right? So we want a slice discovery method that can identify those underperforming slices. And second, we'd like slices that are coherent, right? So for example, on the left, all of the images in this slice show birds on a green background, right? So there's something sort of tying the images together, the fact that all the birds are in front of a green background. But on the right, there's nothing really tying these images together. So we would call the slice on the right incoherent and the slice on the left coherent. So the trouble is, and this is sort of the central challenge that we wanted to address with our research, was we don't really have any idea how well existing slice discovery methods are doing at these two different properties, or like how well they satisfy these two desiderata. This is because it's really hard to quantitatively measure the coherence of the slice. So that was that second desiderata. So traditionally, the way that folks got around this is they either evaluated things qualitatively, so that is, they basically ran the slice discovery methods, and then they sort of looked at the outputs and determined whether or not the discovered slices seemed reasonable, or they did it quantitatively, but on a small number of classifiers. So in order to make meaningful progress in the development of slice discovery methods, though, we kind of hypothesized that it'd be important to evaluate these methods quantitatively and really at scale. Indeed, when we first started developing slice discovery methods, I remember we got kind of frustrated because we felt like it was hard to know whether or not the design choices we were making, the changes we were making, were really leading to better algorithms for lack of a good evaluation framework. Cool. Okay, so now that we've sort of explored the slice discovery problem, outlined it, we're going to introduce the two-part approach to how we sort of kind of tackled some of these issues that in our mind are limiting the adoption and the use of slice discovery methods. So the first thing that we're going to do is we're going to talk about the system, or this framework that we've developed for evaluating slice discovery methods. And then second, we're going to talk about Domino, which is a new slice discovery method that we designed, whose kind of, I guess, the design choices behind it were formed by what we learned from the evaluation framework. Cool. So let's dive in into the evaluation framework first. Okay, so what we first did when we wanted to go about developing an evaluation framework for slice discovery methods is we wanted to get an understanding and make sure that the evaluation framework was representative of the types of slices that one might actually encounter in the wild. So what we did was we surveyed the literature to identify the different types of slices that real-world models tend to fail on. And we identified three major categories. There may be others, but these were sort of the three that we decided to focus on at first. Cool. So the first type of slice is a correlation slice. So a correlation slice occurs when there's a target variable, the y, that we're actually trying to predict, and it's correlated with another variable, c. So the collapsed lung example earlier, this is an example of a correlation slice. The target variable that we wanted to predict was collapsed lung, and it was correlated with the treatment for collapsed lung, which was the chest tube. This led us to perform poorly on patients that did have y equals 1, where they did have collapsed lung, but they didn't have a chest tube. The second type of slice is what we call a rare slice. So this is a situation in which there's, for a given target variable, there are elements in a subclass of y, right? So some subclass c that occur infrequently. So this, I think, also pops up quite a bit. It's basically, yeah, you can think of this basically just a rare subclass of some superclass y. And because it shows up less in the training data, it's possible that the model will perform poorly on it. And then finally, we also explored what we call noisy label slices. So in a noisy label slice, there's some subclass C, so some subset of the examples in a particular superclass that have higher label error rates than the rest of the data set. This can occur for a number of reasons, but one thing might be that maybe the labelers have less expertise in a particular subset of the data, and therefore there are more mistakes in those labels. Cool. So these are the three types of slices that we sort of consider. So given these different slice categories, we want to basically frame slice discovery as an information retrieval task that we can evaluate quantitatively. Okay, so let's sort of discuss exactly how we do this. What we're going to do is we're going to generate a large number of controlled slice discovery settings. So a slice discovery setting is basically just a situation in which you might want to employ a slice discovery method. And then we're going to evaluate how well these different slice discovery methods do. So how do we generate these controlled slice discovery methods or slice discovery settings? What we do is we begin with a base data set. So something like ImageNet would work great here. Basically any data set that contains some labeled metadata attributes. So these metadata attributes are going to be really important for creating the slice discovery setting. So in this example, which is a toy example right here, we have a data set labeled with 3 binary attributes, right? So whether or not there's the presence of a bird, the presence of sky, and the presence of cats. Cool. So what we'll do next is we're going to create a set of coherent ground truth slices. So this is like a subset of the original data set where all the images have something in common. So in this case, in this particular example, we're going to be creating a correlation slice. And so in order to do this, what we're going to do is we're going to pick one of these other attributes, in this case, sky, and we're going to take a look and try to induce a correlation so that there are more examples with some more examples of birds with skies in their background than examples with birds without sky in the background. Cool. So we've resampled the data set to sort of induce or cause this slice to manifest. Next, what we do is we train a model on the subsample data set. And we repeat this many, many times. So what this allows us to do is it creates a large number of these slice discovery settings where, again, we have a trained model and we have a sample data set on which the model was trained. And if you recall from earlier when we were discussing sort of what is the input and output of a slice discovery method, a trained model and a sample data set is exactly the input to one of these methods. So by repeating this process many times, we can generate like a large number of these settings. And again, this allows us to get us to provide better estimates for the performance of these methods. And so we repeated this on the order of about 1,000 times for different slice types and different data sets. Cool. So like I said, the sample data set and the newly trained model, which underperforms on the slice, can then be fed into the slice discovery method. We get the slicing functions. We apply the slicing functions, and then we can evaluate performance. So how well was the slice discovery method able to recover the slice that we know to exist, that we know that the model underperforms on? So remember, in this example, this was birds without a sky in the background. And so what we then do in order to measure this quantitatively is we compute precision at 10. So this essentially measures the proportion of the top 10 elements in the discovered slice that are also in the ground truth slice. So for this correlation setting, in this example, since we set our ground truth slice to be the set of images of birds with no visible skies, we got a precision at 10 of 80%, since there's one image of a bird with the sky in the background. Cool. So in our work, we instantiated this framework across 3 different domains: natural images, medical images, and medical time series, which resulted in a total of 1,235 different slice settings. So that's 1,235 different models where we know exactly which slice the model underperforms. Cool. So now that we've discussed our evaluation framework, we're going to discuss the second part of our work, which is Domino. This is a slice discovery method that was designed specifically to discover coherent and underperforming slices. Cool. So Domino follows a 3-step procedure that we're going to kind of walk through right now. And one thing to note is that the first 2 steps of this 3-step procedure are very similar to the two steps taken in previous works like Spotlight, George, and multi-accuracy that I highlighted earlier. So it's important to note that there's sort of this shared structure across these different slice discovery methods. So we begin by embedding all of the inputs with cross-modal embeddings. So this basically puts the inputs, in this case images, but it could be other modalities as well, puts the inputs and the text into the same latent representation space. So one of the key insights behind Domino is that an input representation generated from cross-modal learning techniques actually encodes a little bit more semantic knowledge necessary for identifying coherent slices. Because remember, one of the desideratum that we outlined at the beginning was that we want slices that actually correspond to some concept where the images have something in common. So for our natural image settings, so settings in which we're using kind of images like ImageNet, Celebe, etc., this cross-modal embedding function can be sourced from large pre-trained multimodal models like CLIP. But for other domains, like our medical image and medical time series data, we pre-trained our own cross-modal embeddings from paired input text data sets. It's important to note, though, that it is not required that the validation data that we're using to evaluate the model be paired. We just need some external data set on which you can train the encoder. Cool. So then the next step is, once all of the inputs are embedded in a cross-modal representation space, we're going to identify coherent regions in that space where the model underperforms. So the way that we do this is we use a simple mixture model where we model the input embeddings, the class labels, and the model predictions. So we call this an error-aware mixture model because it tends to cluster data points by error type, where false positives that look similar are in one cluster, false negatives in a different cluster, etc. And so here again, it's important to emphasize this is a really simple method. It looks very similar to a Gaussian mixture model, except now we're also modeling two additional variables, y for the model's predictions, this is a categorical variable, and then also y hat, which is also modeled as a categorical. Now, finally, this is a step that's unique to Domino. We're going to go ahead and we're going to actually help practitioners interpret the discovered slices. Oftentimes, it's difficult once a slice discovery method has discovered a set of points that it thinks are underperforming. It can be difficult to know sort of what is the thing that ties all of these images together. Usually people resort to just sort of looking at the images in a list and seeing if there's anything sort of that connects them. But I think this process is a little bit subject to confirmation bias. So we set out to try to find another way to help practitioners understand what concept, what's the main idea behind a slice. So in order to do this, Domino generates automated slice descriptions using the text embeddings nearest to the slice in the joint embedding space. So generating these natural language descriptions, I think, was one of the most exciting parts of this work. And it was really neat to see that this actually could work a lot of the time. Cool. So now let's dive in and we're going to kind of show how we used our evaluation framework to validate the design choices behind Domino. So specifically, there are these 3 steps in Domino. There's the choice of using a cross-modal embedding space as opposed to using a different type of embedding space. We want to validate that. Second, we want to validate the choice of our clustering algorithm, the algorithm that actually extracts the slice from the representation space. This was the error-aware mixture model. And then finally, we want to validate how well we're able to actually generate natural language descriptions. And we're going to use that evaluation framework that we discussed earlier in order to do this. So the first question we wanted to answer was, how does the choice of embedding affect slice discovery performance? So in order to answer this question, we compared a number of different embedding approaches and then evaluated precision at 10, how well our slice discovery method was able to recover the known slice that the model underperformed on. For natural images, we compared CLIP, which was a cross-modal embedding space, BIT, which is another large pre-trained model, but it is not cross-modal. And we also compared a random initialization of a ResNet. And we found that CLIP kind of produced was most effective in recovering coherent slices. It was the best at kind of uncovering the coherent slice that we had hidden in the slice discovery setting. Cool. The next question that we wanted to ask was, how does this error-aware mixture model compare to other methods? And we consider a number of different approaches that have sort of been proposed before. There was a number of interesting findings here. We found that the error-aware mixture model, so that simple mixture model that I introduced earlier, did particularly well here. I think there's definitely a lot more room, though, for improvement and a lot more analysis that can be done to better understand the trade-offs between these different methods. So what we're going to do is we're going to actually open source sort of all of the slice discovery settings that we developed, and hopefully people can kind of iterate on it, tune parameters, and see how well they can do in boosting performance here. But we found kind of in our initial experiments that, that using an error-aware mixture model was quite effective for discovering slices. And finally, we wanted to know how accurately can we actually describe these slices with natural language. So here's an example of a real slice that we discovered in a pre-trained ImageNet model from Torch Vision. So this is like a ResNet 50 downloaded from PyTorch Torch Vision. What we wanted to know is, how good is this model at detecting cars? So classifying cars from images in the ImageNet validation set. And when we went ahead and we applied Domino to this slice, this is one of the slices that it uncovered. And if we look on the right, we can see the actual generated slice description. So what did Domino, how did Domino describe the slice that it had discovered? So you can see here from the generated slice description that it seems to be kind of talking about this concept of photos of cars taken from the inside. I thought this was kind of an interesting slice because it was like, oh, that actually kind of makes sense that maybe a model would struggle to classify cars when the photo of the car isn't from the outside. It's a little bit of an edge case, we could say. And it was pretty neat that Domino was able to kind of describe this slice. I think the other important thing to note here is, like, when you get a slice like this, or when Domino discovers a slice like this, it's really important that the practitioner actually be able to understand what the slice corresponds to. Because whether or not this is an issue that needs to be addressed, like how severe of an issue this is, will depend a lot on the circumstance, right? And so it's sort of up to the practitioner or a domain expert to interpret it and say, okay, this is something that we really need to address, or this is perhaps a more acceptable error. Cool. So here are a few more examples. This is taken from the different slice discovery settings that we created. So here, again, the model was trained to predict or detect vehicles, and we created a rare slice where submarines, which are a type of vehicle, were quite rare. The model sort of recovered these as sort of prototypical images of submarines and then labeled it a photo of a submarine or an underway. Another example, and this one was kind of interesting, was we took Celeb A, which is a data set consisting of tons of photos of celebrities annotated with different attributes. And we induced correlations between the attributes. So in this example, we were predicting whether or not the celebrity had black hair, but we correlated it with their wearing eyeglasses. In other words, everyone with black hair was also wearing eyeglasses. And we wanted to see whether or not Domino could sort of discover that the model was underperforming on examples of folks without black hair, but with eyeglasses. And it did sort of, was able to kind of pull this out. And then finally, we did a noisy label slice category. We were trying to detect food, with beverages being a rare slice. We were able to pull that out. Cool. So we also wanted to evaluate these natural language descriptions quantitatively, in addition to the qualitative examples that we saw before. And so what we did was with our natural image settings, so these are like ImageNet and Celeb A, we measured how frequently does Domino include the exact name of the slice in its top description. And so we found that 40% of the time, the first description that Domino returns literally names the slice that we had in mind, the one that we hid. Exactly. So this is a super exciting finding to us that this worked well. Obviously, there's still room for improvement, but it was pretty neat that we were able to kind of get these descriptions. I remember being very excited when I saw that this was working. Cool. So I guess I'm going to conclude here, and I think we have quite a bit of time for discussion, which is great. Wanted to kind of get through this, lay out the groundwork of what we were working on. So just sort of a recap. We introduced this programmable evaluation framework. So this is sort of a repeatable set of steps used to create slice discovery settings, which allow us to evaluate slice discovery methods for underperformance and coherence. And then second, we proposed Domino, which is a slice discovery method that's based on cross-modal representations. Cool. So last little bit, I'm going to plug. We've released the implementation of Domino. You can pip install it, and we're also going to release all of those slice discovery settings. So if you want to modify Domino, if you want to develop your own slice discovery method, this is very much possible, and it should be pretty easy to download. And here to help if you want to try things out and things aren't working for you. Cool. Well, I think that's it. Thanks so much. Again, shout out to my awesome collaborators, Maya, Khalid, my advisors, Chris and James, and our other collaborators as well. This is a really fun project to work on.
Awesome. Thank you, Sabri, for the talk. Very interesting Domino framework for slice discovery. Before we go into Q&A, maybe let's all give Sabri a round of virtual applause. Thanks for the presentation. And yeah, let's open the ground for questions. Does anyone have any question here?
I have a quick one. So I'm not sure if maybe I missed this, but did you try to replicate the experiments on the chest X-ray data set to see if, let's say, you would identify the presence of tubes or not in the images?
That's a great question. Yeah, so what we did was we took Mimic, which has sort of a bunch of different things annotated, which was very, very useful. We weren't doing specifically chest tubes, but we were looking at support devices, which are annotated in Mimic. So a slightly more general category. And yeah, we were basically inducing correlations between the different pathologies, and then seeing whether or not we could recover what the induced correlation was. So kind of, I didn't go into much detail in it. Most of the examples that we were looking at in the presentation were like these natural images, but definitely important to note that, like, yeah, we put a lot of time into developing things or like running experiments on Mimic, and then also on EEG, which was the medical time series as well. And so we were doing similar things there, taking attributes, inducing correlations, et cetera, and then checking whether or not we could recover.
Oh, great. Yeah, I was very curious about that because I've run into issues with that before. So this sounds great to apply then.
Yeah,
Thank
and
you.
that was, sorry, yeah.
Ramon, do you have any more questions?
No, I'm good.
Yeah, I have a question about generating the natural language of describing the slices. You briefly talk about you took the embedding, the word embedding closest to like the slice in the embedding space as the description. Yeah, I wonder how that's done, because like the description is kind of like a sentence, right? But the embeddings are more like words, or is it like an embedding of the whole sentence?
Yeah, that's a great question. So I guess let me answer this in two parts. So first, there's the question of how do we generate a candidate set of phrases from which we're going to pull the description? Because again, like this is not like a generative model. We can't actually like generate a new text. It's just from a collection of phrases, we can select which phrase best describes the slice. And so the way that we did this was we took a large pre-trained language model off the shelf, and we had it fill in basically templates that looked like something like a photo of blank, blank, blank. And so we just said, you know, fill in these templates, Mad Lib style, you know, mass language modeling style. And we generated, say, you know, 30,000, 50,000 different candidates. So we have these phrases. Those phrases are fixed. What we can then do is we embed each of the phrases with Clip. And so to answer your question, or at least part of your question, Clip can embed sort of a full phrase, not just one at a time, not one word at a time. So we embed the full phrase, and we put those all into the representation space. Then, in order to find the description, we take the examples in the slice, we take their embeddings in Clip space, we average them. We actually also then need to sort of subtract out the embedding of the superclass, so like the superclass that the slice is in, and then we dot product that with all of the different text embeddings, and we just take the max across them, and this gives us a description.
I see, makes sense.
Yeah, the first step of generating the descriptions is definitely important, and I think, yeah, that was kind of fun to work on at the very beginning. Sorry,
actually, how do you do that? Like massively generating so many phrases. Do you actually look into? Do you manually do that, or?
Well, yeah, we do it using. I guess you start by generating some templates.
Right.
So the templates we do manually, and that's sort of domain specific. And the templates, we're talking on the order of like 10 to 15 templates. So it's not a large number, or it's not a large amount of manual work, but it is important that those templates are specific to the domain. So as an example, the templates that we used for Celeb A were different from the templates that we used for ImageNet.
Right.
In Celeb A, the templates were a photo of a person blank, 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 or a photo of a blank person blank, blank. Then we take like, I think we just used like BERT off the shelf, and we fill in those blanks, and then we get a bunch of candidate settings, like a photo of a person smiling, a photo of a person, you know, wearing a hat, etc. And we literally just take the examples that are most like the highest likelihood examples from the BERT model, and use those as our candidate set. So there's a mix of some manual work that requires, you know, knowledge about the domain, but then also I would say the bulk of the work is done automatically using a pre-trained language model.
I see. Okay, thanks.
Sabri, nice work. I have just one quick question. Did you try ever the localization of the object in the image?
Yeah, that's a great question. So sort of, I think in the final iteration of the project, we didn't do any sort of localization. In general, it was just sort of like the image has this concept or it doesn't have the concept.
Mhm.
Early on, though, I remember I spent some time diving into some experimentation in this direction, and I actually it was quite promising. I can quickly summarize the way that I was approaching it was when we think about the activations for an image, there's of course like, you could take one vector for the entire image, or you can also consider, maybe at the penultimate layer or, slightly before that in the model, we can take the activation where we have maybe like an 8x8 grid and it's like 512 deep. And so in that situation, you actually have different activations for each part of the image, and you can cluster on those instead. And when we did this, we did kind of get like these nice little like heat maps that look sort of like CAM activation maps, where you could be like, oh, the concept is more located down here versus up here. But I guess one of the reasons why we kind of moved away from that was we felt like sometimes concepts are localized and sometimes they're not. And I think there is a lot of value in localizing the object, but for this first kind of take, we decided to like take a step away from the localization. We said we're going to consider a more general set of slices where the object could be localized, or that it could be something like a dark image where there isn't just like one part of the image. But I think this is an exciting kind of like avenue for future work, like how to like localize specifically where in the image the concept is corresponding to the slice.
Right. And so did you also take a look at the negation and uncertainty kind of concepts?
So what expand on that a little bit?
So imagine like you just mentioned replying to these questions that you have the templates and you are getting the words predicted and you're just filling the templates, right? So imagine that in radiology, for example, like there is a tendency that people always write that imagine like the lung lesion doesn't exist. There is like no lung lesion, like no pulmonary embolism. So this kind of negation or the uncertainty, right? Like it's uncertain that if there's a pulmonary embolism or not. Did you try to see if that kind of uncertainty or negation is also captured by your model, or it's only like positive finding?
That's a great question. Yeah, it can capture negation. So when we were generating the sentences, because of those like those masks that are meant to be filled in by the model, it'll often just fill in like not or something like this. So you do get candidates that have it. And then similarly, when you're doing the slicing, frequently they'll be like, I don't know, in celeb A, for example, there might be a slice of folks wearing eyeglasses and folks not wearing eyeglasses, right?
So I was mainly curious with your celeb A example, exactly. Like, for example, if a folk is like with black hair but wearing eyeglass, and black hair not wearing eyeglass,
Exactly.
You try to see generating this kind of example with like not or uncertain.
Yeah, that's a great point. And in particular, in that celeb A example that I had up there, the slice that it found was, not black hair, like wearing eyeglasses, but another slice that it's going to perform poorly on is black hair, not wearing eyeglasses. And so, yeah, we found that it is able to do that, but I think there's also potentially worth like experimenting with, explicitly injecting the negations into the templates, right? So that's another option too. Like if you know that you need negations, you can put that into the template.
Yeah, and this is particularly interesting in the sense of radiology. Imagine that according to the rule, like that you have to negate some of the important radiology finding if they're not present within the exam, right? For example, if you do a chest X-ray, you have to mention that it isn't either it's a completely normal chest X-ray or the patient doesn't have pneumonia, because probably the chest X-ray was ordered for pneumonia. No?
Right.
So,
yeah, exactly.
So I think that would be kind of interesting to see how the model behaves, or particularly on this kind of like no or uncertain keywords.
That's a great point. And I wonder, like, so as we're sort of releasing all these different examples. Unfortunately, we're focusing so far, like in terms of the public release of the slice discovery settings, we're focusing on the natural images just because of like, I don't know, privacy concerns with the medical data and stuff. But one of the things that I wanted to emphasize was being able to stratify the slice discovery settings, because I didn't want like the conclusion to be, oh, this slice discovery method is better writ large. You know what I mean? Like it's always going to be a trade-off between the different methods. And I think there could be an interesting thing here, like where one of the strata we observe is, oh, this slice discovery method is actually pretty bad at negations. Even though it seems like it's really good overall, it's pretty bad at negations. So I think that's actually a really good idea. And we should like maybe annotate the slice discovery settings. Like these ones are a negation, these ones are not. And then we can kind of compare performance in those two groups.
Right.
All right. Any other questions from the audience? Sabri, I wonder if you have experimented, because I know like all the experiments were done in a controlled setting, right? You control the setting. I wonder if you have experimented with like other data sets that have been shown to have this issue in the literature.
Yeah, that's a great question. When we were starting the project, and as I mentioned, we were running into this issue where we felt like it was difficult to make progress because we didn't know whether or not the method was succeeding. There were sort of two options that we considered. One was kind of surveying the literature and getting a bunch of real examples. And I still like that approach. We ended up not going with it because we found that it was like hard to like exactly regenerate the exact examples that we found in the literature. But I still, I don't know, I think that is one limitation of our work, is that we focus primarily on these controlled settings. Granted, the control settings, we tried our best to like make them mimic or resemble what we found in the literature, like real examples, but this definitely is a limitation. And so we actually released just a couple days ago a couple of blog posts where we start applying Domino to like real models that people actually might use. So for example, I showed that example of like photos of cars taken from the inside. And this was like a Torch Vision ResNet 50. This is a model that probably everyone has downloaded at one point or another. So that's been really fun, like actually applying it to real models. I'm also excited about potentially like running this on models that are offered by different like cloud services. So things like image recognition, facial recognition, to audit those models as well. I think also shout out to Greg Dion's Spotlight paper. In their paper, they do a nice job of taking Spotlight, which is another slice discovery method, and they apply it to a bunch of public models. So that sort of was their way of evaluating things, which was slightly different from the way that we approached it, which was more like quantitative, but synthetic, or not fully synthetic, but like controlled, versus they were kind of applying it to real models. So that would be a cool paper to check out. It's cited in the paper, but yeah, it's called The Spotlight by Greg Dion and others.
Yeah. All right. If there is no other questions, let's thanks Sabri again for this very interesting presentation of Domino. Thank you everyone for joining us today. We will upload the recording of this talk later to our YouTube channel. And yeah, see you next week at the same time, 1 o'clock.
Awesome. Thanks so much for having me.
Thank you, Sabri.
Thank you.
Bye, everyone.